Hello everybody. So today I will talk about the system design of Uber and I will talk about the scalability specifically. So I've already talked about the high-level design, which looks like this, and also I finished the deep dives, like how I can, implement the matching process with the strong consistency, and also I talked about the geospatial indexes. So I decided to use Redis H2. Okay, so based on this design, I will think of the scalability. So in the non-function requirement, I specified like this. Scalable to 100 million daily active users and 15 million writes per day and can handle spikes. So I will update my design to satisfy this. Okay, so based on this number, I will do the back of envelope estimation first. So I will write it here. So I will talk about the scalability from three perspectives. So number one, throughput. Number two, spike of the throughput. And number three, the storage size. So for the throughput, so when I think of this design, firstly I can say there are 5 APIs: create, fair estimate, make request, and fetch result. So these three are about the request of the write. So I will quickly calculate how many requests are made. Sorry, how many writes are initiated every second, and then I will think of this and this backward. And also for driver answer request, yes, this is I can say because in a design, I will give 1 minute of chance to the write to be matched. So for each driver, he's given 5 seconds of the chance to match or not. So in total, one write should require up to 10 or should say 12 driver's answers. So I will calculate this 2 from the number writes per sec. And for update location, this is a completely different one because this is a kind of short polling. So yeah, no matter if the user is writing or not, or driver is writing or not, the status should be updated every 5 seconds, for example. So I will separate this in perspective of the access pattern, and I will calculate how many times, how much requests per sec this API is called with. Okay, that being said, so I first restart with the write per sec. So 15 million writes per day is because 1 day is around 10 to 5 seconds. I can say the 150 writes per sec is created. So about okay, so let's say only half of the user okay, let's say fair estimate is created 4 times. So I should say create fair estimate is created, and then 50% of the user makes a request and 50% of the request is accepted. In this case, with that number, create fair estimate, this is 600 requests per sec. And this is actually not so heavy because typically the PostgreSQL can handle around 10K to 50K of read request and 10K requests per sec of write request. So 600 is much lower than that. So PostgreSQL wise, it's fine. An API gateway, this is a cluster of servers, so this can be internally scaling out. And write service, so because this request is stateless, so I can use a scale out for write service. So according to the CPU usage or memory usage or amount of the traffic, this write service can be horizontally scalable. Yeah, so in that way, I can handle the request, 600 requests per second request of create fair estimate API. And for make request, as I said, 50% of 600 is 300, so this is completely handleable again. And for fetch result, this is a kind of tricky because for each request, which is 300 requests per sec, result is fetched multiple times from the client because we decided to use the short polling here. So let's say the user has to wait 1 minute and it does a short polling every 5 seconds or 6 seconds. It means that the one write needs 10 times of short polling. So I can say this fetch result API call is now 3000 requests per sec. So 3000 requests per sec is again, this is completely handleable. Yeah, based on the number I said, 50k requests per sec is handleable for read queries of PostgreSQL. So this is totally fine. Good. And driver answer request. So the same calculation can be done for this API. So for one request, up to 10 driver answers are submitted. So it up to 3000 requests per sec. So which is totally handleable again. Okay, so that's the numbers I can say from this. So I will quickly write it down. So create and make request. So this is 300 per sec. Sorry, I should have written it first, actually. So fetch result. And driver answer request. Okay. So now we talk about the update location API. So this should be updated by, the location should be updated by the client, either user or driver. So let's say there are 100 million data active users and each user is online. So online means user opens the app and searching or using the app, and driver, in case of driver, he's driving. Or I should say the status is available or matching or matched. So on average, let's say each user is available for, let's say, 4 hours. Yeah. So 4 hours, which means that, let's say, the request is made every 5 sec. So how many times each user makes a request? So 720 times. And there are 100 million data active users. So I can say this should be 1 and billion, 72 billion. Okay, sorry, 72 billion times a day, which is, I will divide it by 10 to the 5, and 720,000 requests per sec. Yeah. Okay, so this is it. So 7, let me check. So 10, yeah, this is correct. Okay. So this is the ROT. So 720k requests per sec. So when I take a look at this, the update location API goes through update location API call goes through API gateway, which can be scalable, and then location service. Again, this is horizontally scalable because this request is, stateless. And then updates the location in Redis. So I can say this Redis is the heaviest one. Heavy loaded them, and I have to think the most. So the Redis is, in-memory database, so it can handle relatively more queries than PostgreSQL, like 10 times or something. Yeah. That being said, the search query is, so in my understanding, search query is kind of heavy because what it does is kind of complicated, as I said before. So around 10k requests per sec. And I can say update query is much faster, so it can handle 100k requests per sec. Because as I said, what it does is updates the longitude, latitude, data, attribute, and also the recalculates the hash value and store it in the B tree. So update query, it performs better. So what I'm thinking is update query. So I can say 720k divided by 100k. So when I think, I will think of doing the sharding. Yeah. So around 7.2 shards are needed. So obviously I can do the sharding based on the continent. So I can say the users in America and drivers in users in America and drivers in Japan, they don't have to know each other. Obviously, they can be separate and they can be independent to each other. And also I can say in the data governance perspective, the location data of, European countries must not be stored in the database in Japan or America. So I cannot, in that perspective, also the sharding is definitely needed. Yeah. So my solution here is to use the sharding according to the continent. Yeah. Actually, this makes it easier because even in Europe, the drivers in the UK and the driver locations in France, they can be independent. So yeah, maybe I can think of this, for example, by the country, country level. Yeah, for some countries, if the user doesn't go beyond the, border line, like America and Mexico. I don't know. So that's another thing I can think of when I think of this sharding. Okay, so I can do the sharding of the Redis. Good. And maybe I have to think of the request worker too. So as I said, there are six 100 writes per sec. No, sorry. Request is 300 requests per sec. So request worker handles 300 requests per sec. And based on the operations it does, it firstly makes a query to the Redis. So I can say this is 600 requests per sec. Because we decided to do the sharding, maybe like 10 shards, each shard has 60 requests per sec of location query. So this is completely handleable because search query is 10k requests per sec. Yeah, so this is totally fine. And also it does, makes a request to PostgreSQL 2, for example, to get the log of the driver or something like that. So again, it is up to 600 requests per sec, so PostgreSQL can handle it completely. So good, Supergets worker, this is one is fine. Yeah. So I don't discuss about the throughput of notification service because I can say, probably not the concern of our system. Yeah, for now. Yeah, so maybe, but obviously Google Firebase messaging API and our push notifications API, it's totally handleable. It can handle it, of course. So yeah, I can say this system is now scalable to the required throughput. Oh, and one more thing I want to say is I can think of using the read replicas of the PostgreSQL. This is because, as I explained, read queries can be handled with only single PostgreSQL server. But I can introduce read replicas for the spike, firstly, and also for the torrents. So with setting up the automatic failover, the read replica, when the primary node goes down, the read replica can get promoted to the read replica so quickly. So that's why I think using read replicas is also a good idea here. And also for Redis, actually this has the read replicas. Yeah. But of course, this read replica is asynchronous, replication. So it just guarantees the eventual consistency. But as I said here, aside from matching, eventual consistency is fine, so I can use the read replicas. Okay. Oh, and one more thing. So when I say sharding in Redis, it means that I use Redis cluster. Yeah. So with Redis cluster, I can specify the sharding key, partition key, and I can use the kind of continent ID calculated from longitude, latitude, and now Redis cluster internally does the sharding. Sorry, one quick correction. So I just searched this with, Redis cluster sharding key, and it says Redis cluster doesn't use separate configuration or data level shard key. Instead, it uses algorithmic sharding where each individual key is hashed using some algorithm. So it means that Redis cluster internally does the sharding with the kind of partition key calculated from longitude latitude, which doesn't take the country borderline into the consideration. So instead of using the Redis cluster, I would say I will use the custom 10 shards. which means that in the application level, okay, so we set up 10 Redis clusters, and in the application logic, it decides which longitude-latitude pair belong to which shard, which means which continent. So yeah, the thing is, I cannot use the Redis cluster here, but I do the custom sharding logic in the application level. Okay, so now I will talk about the spike. So in case of the Uber, I will think in which cases the spike occurs. So the possible scenario is, let's say there is a concert or baseball game in the stadium, and the many of the audience drink a lot, and because they took the alcohol, they can't drive. So they, request the Uber ride when the game ends. And let's say there are 10,000 users or maybe 20,000 users request the ride at the same time. So in that case, there's so many requests coming from the audience in that specific area. So I can say this is a spike. But the interesting thing about this is kind of the spike in Uber is quite, local. So in some local areas, there are spikes, but there isn't a kind of global spike. Yeah. So okay. That being said, so what it means is that even though I calculate the number, it doesn't become 10 times because spike is local only in the specific area. So because so far I did the sharding of Redis in the continent level, of course the Redis instances which is responsible for other areas are not affected. Yeah. And also I can say it doesn't become literally 10 times because specific user drivers location no. Sorry. I can say location data doesn't have any spike because it already updated every 5 seconds. What spikes is, the thing which has spike, the APIs which have spikes is these three: create fair estimate, make request, and fetch result. And also this request worker. Yeah. So I will think of this. Yeah. And of course, as I said, the spike is quite local, so I don't think it makes the overall request per sec to 10 times or something. Yeah. But just in case, I will think of the extreme case that I need a scale out. So for API gateway ride service, this can be scalable. So for ride service, I can use AWS auto scaling so that if there's so many requests, it can scale out. But maybe what I can do is, okay, so as long as AWS auto scaling is correctly set, it can handle the spike. But of course, booting up the server takes some time. And maybe there are some cases that we don't want to miss the right request at the time. So considering that, what I can do is introducing the queue here, asynchronous queue. So write request or fair estimate request are stored here. And actually, I can think of independent queue for each. Fair estimate request and request. Yeah. And driver response create match. Okay, so I would say for create fair estimate and create request, I use I introduce the queue and handle it here. But for the driver response, I don't create the queue and I still make this synchronous APIs because the driver's update response should be reflected to the right matching status immediately. So maybe I have to pay some money for AWS, but maybe I will do the hot standby servers for this purpose. But I can say even if the request becomes so many times, it doesn't mean there are so many drivers at the same time. So the spike for this driver response is, I can say, more, calm some request APIs. So this is the fair estimate queue and request queue. So the write service pushes this. But as I said, yeah, of course we can separate the service if I do this. Maybe I will do it. So maybe this makes more sense actually. Okay, so now the worker fetches the request or fair estimate request and works on the same thing I explained. Like this. Yeah. So now I can say even if there are so many fair estimate requests or write requests, there is a queue which works as a buffer. So now yeah, it doesn't. Okay, so even if there is a kind of time lag in the auto scaling of the write service servers, the requests are not lost. Yeah. Because, sorry, what write service does is just pushing the message into the queue so it can handle more requests. And also for PostgreSQL, it doesn't overload it with the request because this front-end queue, sorry, these two workers can, batch the request. I mean, okay, let's say this worker works every 1 second, and all the requests or fair estimate requests which were made in that 1 second should be bulk written to the PostgreSQL. So the throughput of the write queries are reduced and it becomes a bulk write query. So now database is less loaded now. Okay, so this is how I can handle this. And for request worker, I can scale out this worker because each worker is responsible for only single write. request. So they're doing independent works, so I can do scaling out. So I'll be clear on this part. So change that the capture is pushed into the queue, like Kafka. And now this request worker fetches from this request worker. So for this, let's say using Kafka, I can use the partition key as write ID. Yeah. So in this way, the messages in each partition in Kafka are even. And yeah, so that's something I can do for Kafka. And of course, basically in Kafka, there is up to one consumer can handle one partition. So by doing say partition, multiple workers can, handle, handle the write request. Okay. I'll just be clear for this front end fair estimate queue and request queue, the partition key can be ID, which is kind of UUID generated in the server when pushing the message. Yeah. So what it internally does is there is a local spike, but local spike is completely distributed into multiple partitions. So it kind of mitigated by, distributing it to all the partitions. So that's the basic idea. Okay. Yeah. So that's it. Oh, and there's one more thing I'd like to mention quickly. So I said there isn't a spike on this update location API, but obviously this is the most, heavy loading API, and actually I can use adaptive polling here to reduce the, load in general. So let's say user is waiting in the traffic light or driver is waiting in the traffic light. In that, let's say 1 minute of period, the location update is not necessary. So the client side can decide if the update location is needed or not. So yeah. And also in case of the driver, if the car is moving fast, maybe it should update the location more frequently. And if the car is on the local road and if it's moving slowly, the interval to update the location can be longer. Yeah, so that kind of adaptive polling can be used to reduce the load of location update API. I will quickly write it here. Okay. Now I will talk about the storage. So we have two databases, PostgreSQL and Redis. So I will start from PostgreSQL. So firstly, we have user table and driver table. I'm almost pretty sure this isn't so big. I think this can be hundreds of gigabytes of size, but I will do a quick estimate here too. So let's say there are 100 million data active users. Let's say there's 300 million users in total. And let's say each data has 100 bytes. So in this case, so kilo million, so byte becomes kilo mega. Sorry. So it becomes 30,000 megabytes, so 30 gigabytes. Okay, so yeah, this is completely, only single PostgreSQL can store this data, because nowadays around 512 gigabyte of data can be stored in the AWS Aurora PostgreSQL, for example. Okay. So I will talk about the fair estimate request driver response match. So in terms of the ride, I will calculate how many rides there are in a year. So there are 50 million rides per day. So I multiply with 365. So it becomes around 5,000 million. So billion. So 5 billion rides per year. And I assume that in total, 1 kilobyte of data is created for each ride. So this includes the numbers of fair estimate record, and of course the request, I should say. And yeah, okay, I can say. So as long as the acceptance rate, or I should say matching rate, is not so low, I can assume that fair estimate table is maybe twice or three times. Okay, sorry, wait a minute. How can I say? I'm thinking how I can express this. Fair estimate. Okay, let's say, yeah, fair estimate is created twice and request, sorry, four times. Request is created twice of this actual right number, and driver response is created two times, and match is exactly this number, so 5 billion. Yeah, they're in the same order, and let's say each data stores 1 kilobyte of data. So in that case, 20 gigabyte, yeah, of data. Okay, good. So this is 10 gigabyte. This is 10 gigabyte. This is 5 gigabyte. So in total, this should be around 50 gigabyte. Yeah, 45 gigabyte. So in 10 years, this becomes 500 gigabyte. Wait, correct? No, this should be terabyte, right? Mega, giga. Yeah, 20 terabyte. Okay. Yeah, so in total, it becomes 50 terabyte of data per year. So it can store around 10 years of data. But something I forgot to mention here is, just like the Redis, I should do the sharding of PostgreSQL, because, as I said, the users, therefore, there are two reasons. Number one, for data governance reason. The data for European users should not be stored in the American database, and vice versa. So database should be separated and stored in each region. Yeah, so we need the kind of sharding here. So, and as I said, maybe we do the 10 shards. So 5 terabytes for each region. So it can store around 100 years of data. Yeah. And yeah, so data governance is the first reason. Yeah. Okay. So yeah, actually, so this is now scalability of the storage. There isn't an issue on this PostgreSQL, I can say. For the Redis, there are in total wait, so 100 million direct, so as I said, 300 million users. And let's say each user data has 100 bytes because each user has only longitude, latitude, and geohash value in this Redis. So in total, there should be 30 gigabytes. Yeah, because Redis can store, let's say, 500 gigabytes of data in the memory, so this can be completely handleable. But one thing I have to make sure is that the historic data of the location should be saved somewhere. Because if there is a kind of incident or crime, that data is quite important. Yeah. So, yeah. So, what I can do for that purpose is when, so actually, okay, so this is not included in the non-functional requirement. So to be honest, I don't have to discuss that further, but I will just add this one. So if we need the historic data for each user's location, I can introduce the Kafka here and do the deal write from location service. Yeah. And I will do this update location as the best effort. Yeah. Because obviously, even just because of the failing this should not stop the whole application. Yeah. So what I can do is when location is updated, it updates the Redis location, and also it should update, sorry, enqueue the new location into Kafka, and there is a worker which stores the data into, let's say, S3. The reason why I use S3 is because it's cheap. It can be used as the cold storage. So I will use that. Okay. I will abstract this a little bit. So this is now stored into the S3. Like this. Okay, so this is it. Okay. So now I've talked about the spikes. Sorry, storage size of Redis also, and as the bonus, I talked about the location saving, historic location saving feature. Okay, so that being said, I finished my today's system design practice. Thank you so much. Bye.